The automotive industry is the most important application area for composites in Europe. As we have already learned, composite materials are rapidly transforming industry around the world, and the automotive sector is no exception. As we continue to innovate in the design and production of vehicles, composites are becoming increasingly essential due to their unique properties such as lightweighting, strength, durability, and cost efficiency. In automotive applications, two types of composite materials are most commonly used: glass fiber reinforced polymers, GFRP, and carbon fiber reinforced polymers, CFRP. GFRP is widely used in automotive applications for its resistance to corrosion, low fabrication costs, and long service life. It offers a smooth surface finish and favorable balance between strength and impact resistance. In terms of lightweighting, GFRP can reduce the mass of an automotive component by approximately 25 to 35% compared to traditional metals. Mechanically, GFRP exhibits excellent internominal shear strength, even at elevated temperatures. This makes it suitable for under-the-hood components exposed to thermal stress. Furthermore, it has a low thermal expansion coefficient, which minimizes dimensional changes due to temperature fluctuations. CFRP is distinguished by its exceptional specific stiffness and strength, far surpassing those of conventional metals. CFRP components can reduce vehicle mass by 40 to 70% compared to metal alternatives, offering substantial improvement in fuel efficiency and emissions reductions. For instance, replacing steel with carbon can lower vehicle weight by 60%, increase fuel efficiency by up to 30%, and cut CO2 emissions by 20%. Mechanically, CFRP provides a high stiffness and tensile strength, with continuous fibers allowing for anisotropic tailoring, enabling material properties to be aligned precisely with load directions. It also exhibits superior fatigue resistance, maintaining performance under repeated stress. In crash scenarios, CFRP can absorb impact energy through controlled failure mechanisms, enhancing crashworthiness. CFRP crash tubes have demonstrated better energy absorption than equivalent steel structures. The manufacturing of CFRP components, although adapted from aerospace technologies, remains complex and costly. High-pressure resin transfer molding and automated fiber placement are being developed to reduce cycle times and enable high-volume production. Despite these advancements, the high material and processing costs remain a barrier to mass-market use. Historically used in motorsport and high-performance vehicles, CFRP is now increasingly found in mainstream electric and luxury vehicles. Composite materials are used in a variety of automotive components, including body panels, bumpers, doors, hoods, and interiors. Their ability to reduce weight while maintaining or improving strength is a key reason for their increasing use. GFRP is gradually used for impact-absorbent automotive parts, such as bumper supports or structural elements like door modules or car roofs. It is also being explored for engine components as a replacement for metal due to its mechanical performance at elevated temperatures. Other applications include trunk lids, air deflectors and spoilers, frame for windows, sunroofs, air intake manifolds, front-end grille opening panels, battery casings and covers, lamp housings, heat shields, and pillars. Initially used in high-performance racing cars, CFRP is now present in modern urban cars, particularly in the passenger compartments and structural elements of a vehicle chassis, such as cabin frames, door seals, transmission tunnels, roof reinforcements, B-pillar, C-pillar, and the rear parcel shelf. It is also used in body panels. Other applications are semi-trailers or trucks, motorsports, and passenger trains. Examples include CFRP monocoques in sports car and structural adhesives using CFRP for seat anchor and seat belts attachments. CFRP is being explored for various automotive components to achieve significant weight reduction and improve performance. While the proportion of composite materials in an average car varies, it is estimated that up to 20% of a car's weight can come from composites, with some high-performance sports car utilizing up to the 50%. This proportion is steadily growing due to the material's advantages in weight reduction and performance. Composites play a crucial role in improving vehicle sustainability. By reducing the weight of a vehicle, composites contribute to lower fuel consumption and, in turn, lower CO2 emissions. A 10% weight reduction in conventional vehicles could increase fuel economy by 6 to 8% for internal combustion engine and 10% for electric vehicles. Taking this into account, the use of composite materials in standard cars can increase energy efficiency by 12–16% for combustion engine or 20% for electric cars. Composite materials are playing an increasingly vital role in the automotive industry, offering benefits in terms of performance, fuel efficiency, and sustainability. As the demand for lightweight, high-performance vehicle grows, composites will continue to be a key material driving innovation in the sector. Electric vehicles are considered composites intensive. In recent years, applications in the e-mobility sector have increasingly been added, particularly in the area of battery housings and covers, as well as charging infrastructures.